So let's suppose we are given a thin uniform rod and we want to find what the center of mass of that uniform thin rod is. In fact, we want to show that the center of mass of our uniform thin rod is exactly at the center. So before we begin, let's define what linear mass density is. Linear mass density of our object is simply the total mass of that object divided by the total length of our object. So let's suppose we have the following uniform thin rod, and it lies along the x-axis. So it begins at the point x equals 0 and it ends at the point x equals L. So the entire distance, length of our rod is given by a lowercase l. So that means if we define the linear mass density and represent the linear mass density with the Greek letter alpha, that means alpha, linear mass density, is equal to the total mass of the object, capital letter M, divided by the total length. And we can rearrange this equation and solve for M, the mass. So mass is equal to alpha, our constant, multiplied by L, our length of the rod. And let's label this equation as equation 1. We're going to use it in just a moment. So let's begin by dividing our rod into infinitely small units of mass dm and length dx. So here's one specific unit, one specific length. It has length, infinitely small change in x, and mass, infinitely small change in mass. Now from equation 1 we can deduce the following equation. So because mass or the total mass is equal to our constant, linear mass density constant, multiplied by total length, we can say that an infinitely small change in mass is equal to the same constant alpha multiplied by infinitely small change in x. Now, because our rod is assumed to be thin, we need to find the x-coordinate of the center of mass. Because this object, the rod, lies along the x-axis. So x, center of mass, is equal to 1 over m, where m is the total mass of the object, and we take the integral from x equals 0 from this position to x equals L to this position of all of these small sections. So x multiplied by dm. Now, notice that we can replace dm with alpha times dx. So we take this and replace it with alpha dx. Why are we replacing it? Well, because we need to have our integral in terms of dx. So now we get 1 over m integral from x equals 0 to x equals L, alpha, our linear mass density, times our x, which we get from here, multiplied by dx. So now we have the following result. And notice the alpha is a constant, so we can take it outside the integral. And we have alpha divided by m of the integral x equals 0 to x equals L of x dx. So we integrate and we have x squared divided by 2. Now the constant goes on the outside and we have to integrate from x equals 0, or evaluate the integral from x equals 0 to x equals L. So the 0 term disappears and we're left with alpha times L squared divided by 2m. So this L was simply plugged into the x here. Now, notice we can take this equation and plug this result into the alpha, so we're left with m divided by L multiplied by L squared divided by 2m. So the m's cancel and one of the l's cancel, and we're left with L divided by 2. So we see that the center of mass of our uniform thin rod is exactly in the middle. It's L divided by 2. It's exactly in the middle of the rod.